This water is made of molecules. The cup it's in, the camera I'm filming this on, even you and I are made of molecules. Hi, my name's Cailyn, and I'm a science student at the University of Waterloo. And in this video, we're going to talk about two classifications of molecules, polar and nonpolar. Here, I have two very different molecules. This is a cup of oil, and this is water. When I add the oil to the glass of water, you can see that they don't mix. But why is this? Well, the oil is nonpolar, and the water is polar. Water molecules are made of an oxygen atom and two hydrogen atoms. The oxygen atom is more electronegative than the hydrogen atoms, meaning it pulls the electrons closer to itself. This creates partial charges. The oxygen becomes slightly negative, while the two hydrogens become slightly positive. When you have a glass of water, the molecules are attracted to each other and arrange themselves so that the slightly negative oxygens are closer to the slightly positive hydrogens of an adjacent water molecule. Here, I have a coin, and you can see that as I add drops of water to the coin, the bubble gets bigger and bigger until it looks like it might explode. This is because of the attraction between the water molecules, creating surface tension. Nonpolar molecules don't have a net charge. This can be for a couple of reasons. If a molecule is made of all of the same atoms, like this fluoride molecule, it is nonpolar because both atoms have the same electronegativity, so neither atom is hogging the other's electrons. This is also true for carbon dioxide. Even though oxygen is more electronegative than carbon, because this molecule is symmetrical, the oxygen atoms are pulling equally on the carbon atom in opposite directions. Think of it like a game of tug-of-war. If both teams are equally matched, the rope doesn't move anywhere. That's like a nonpolar molecule. A polar molecule would be like me playing tug-of-war with my small dog. Okay, so now we know the difference between polar and nonpolar, but that still doesn't explain why our oil doesn't mix with our water. To understand this, we have to understand something called like dissolves like, meaning nonpolar molecules dissolve other nonpolar molecules, and polar molecules dissolve other polar molecules. When you mix a nonpolar molecule, like oil, with a polar molecule, like water, the water molecules push the oil molecules away because they would be much happier interacting with themselves. When you mix a polar molecule with another polar molecule, like this table salt, also known as sodium chloride, with water, the salt dissolves. This is because the water molecules are attracted to the salt and break down the salt into its ions. The slightly negative end of the water is attracted to the positive sodium ion, while the slightly positive ends of the water are attracted to the negative chloride ion. Essentially, the salt is dissolved because the water surrounds the chloride and sodium ions. This is called an aqueous solution, and the dissolved ions are called electrolytes. You might be more familiar with this term when you think about Gatorade, which is also an aqueous solution with dissolved electrolytes, albeit a tastier one than salt water. Okay, now let's get to the fun part. For this experiment, we are going to make fireworks in a jar. You are going to need oil. This is just regular vegetable oil, a jar of water, a small cup, I'm just going to use the one that the oil is in, a fork, and some liquid food coloring. In the small dish, add about half a cup of oil and drop in your food coloring. Use the fork to break up the food coloring into smaller droplets. Now, add the oil and food coloring mixture to the water and watch. I hope you had fun learning about the science of solubility and have even more fun experimenting with your fireworks in a jar. And I'm albeit a more tastier one. A more tastier one? A tastier one.
No.